Hello, everyone. Welcome to lesson 25 of Calculus 1. Today, we're going to talk about a very important application of derivatives, which is known as optimization. So many times in practice, if we can model something with a function, we want to find where this thing is at its maximum or at its minimum. So for example, if you found a function that models the profit of a business, you would certainly want to maximize this profit. And sometimes if you have some kind of curve and you want it to be close to a particular point, you want to minimize the distance between those two. So depending on the situation, you may be interested in finding the maximum and minimum of a particular function. So what we're going to do today is we're going to look at some sort of applied problems where we need to do just that. Now, this is another difficult topic in Calculus 1, but just like curve sketching and related rates, this topic has a sequence of steps that you can follow every time to get where you need to go. So the first step I would recommend is I would draw and label a picture. So oftentimes the act of drawing a picture helps us visualize the problem, and it helps us label all of the necessary variables that we need and we are interested in finding. All right, step two. Step one helps us do this step, which is find an equation to optimize. So for example, if we're interested in profit, we probably should write down an equation representing profit so we can find the maximum. In many of these optimization problems, there will be more variables than strictly necessary. So since we're only doing single variable calculus here, we need to eliminate variables from our equation that we got in step two until we only have a single variable remaining. And we'll often do this by using the extra information that they give us in the problem. And then finally, once we eliminate all the variables, we have a single variable equation, then we can take the derivative, differentiate, and find the extrema. All right, so we've definitely done this in a few different lessons here. We just take the derivative, we find our critical points, and then we see if those are maxima or minima. Now, also like the curve sketching and the related rates problems, these problems may seem different every single time, but we're essentially going to follow the same steps every time we do an optimization problem. All right, now the rest of this video is going to be practice. We're going to just practice doing this right here. All right, so our first example, suppose an open box, so a box with an open top, is to have a volume of 36 and its length is twice its width. So these are the conditions we need for the box. Find the smallest surface area for such a box. All right, so perhaps when we're making this box, we want to make it with the smallest amount of material possible, yet we still need it to have a volume of 36, and we still need its length to be twice its width. All right, so let's go ahead and draw a picture. Let's do step one here. So I'm going to draw this box, and notice that I'm making it longer than it is wide to represent what's going on here. So this is the length, this is the width, and then we'll call the height h right here. All right, so we've drawn our picture and we've labeled it. Now what we're going to do is we need to find an equation to optimize. Now the equation we want to optimize here, since we're interested in, is the surface area equation, since we want to find the smallest surface area. So I'll call that equation A for area. And the surface area for an open box, so this top here is going to be open, is the material for the bottom, which will be length times the width. Then we have the height times the length for this side and for this side right here. We have 2 length times height. And then we have the two ends of the box here. We have 2 height times width here. All right, so we found an equation. That was step 2. Now, step 3 means we need to eliminate some variables here. Now, we have 3 variables happening here, but we really can only deal with 1. Let's use the information that was given in the problem to eliminate some of these variables. The first thing we notice is that the length is twice the width, right? So every time I see an L in here, I can replace it with 2W. So doing that, I end up with 2W squared plus 4WH plus 2WH. And I can simplify this, of course. This is 2W squared plus 6WH. All right, well, that's all well and good, but the problem is we still have this H right here. So we need to use our other piece of information. We know that the volume of this box is supposed to be 36. So 36 is our volume, and the volume of a box is length times width times height. Now we already know that we can write the length as 2W, so we shouldn't be seeing any L's anymore. And then what we can do here is we can solve this for H. So if I divide by 2W squared, I have 18 over W squared is going to be H here. What was the purpose of that? Now every time I see an H in my equation over here, I can replace it with 18 over W squared. So now my area is 2W squared plus 6W times 18 over W squared. And when we simplify this, we get 2W squared plus 108 over W when one of these W's cancels. All right, now we've completed step 3. We've eliminated all but one of the variables here. Now step 4, the final step, is we're going to differentiate and find our extrema. And compute dA dW here. So I'm going to do the derivative of 2W squared and get 4W. And I'm going to do the derivative of 108 times W to the -1, which this is, and we'll get -108 divided by W squared. All right, so there we go. Now remember that extrema can only occur where we have a critical point. And a critical point can only happen where our derivative is undefined in the domain of the function or 0. Now we see a place where this derivative will be undefined. That will happen at W equals 0. But the thing is that W equals 0 doesn't really make sense with this problem. And why is that? Well, if W was equal to 0, it wouldn't have any width at all. So that doesn't really make sense for a realistic box. So we're going to ignore that critical point. It doesn't make any, that doesn't make physical sense with our problem. Now that's the only place that this could be undefined. So let's go ahead and set this equal to 0. So I'm going to add this over here and then multiply up the W squared. So we have 4W cubed is equal to 108. And then 108 divided by 4, that will be 27. And finally, the cube root of 27 is 3. So now we know what our width has to be to optimize our surface area. It's going to be 3. Now, if we were trying to be extra careful here, what we could do is we could plug this in to our dA, or we could take the second derivative and use something like the second derivative test to help us see if this is a maxima or a minima here. But this is going to end up being a minimum for this problem. You end up getting W equals 3 right here. All right, and then what we're going to do is we're going to take this and put it into our surface area equation, which was back here. So this means that our surface area is equal to 2W squared. So it's going to be 2 times 3 squared plus 108 divided by 3. All right, so this is 18. 108 divided by 3 is 36. So we end up with 54 as our smallest surface area. Now watch out for this. Some problems will ask you to find the actual quantity, like we did here, 54. But other problems will ask you to find the dimensions that will minimize or maximize something. So if they wanted that, we would have to give width is equal to 3, and then the length would necessarily be 6, And then we could solve for the height, which will be 2. So we would have to provide 3, 2, and 6 as our answer for this. But they didn't ask for the dimensions for this problem. But be sure to read the problem and make sure you're giving them what they asked. All right, that is our first example here. Why don't we go ahead and do 2 more? All right. Our next example is, suppose a farmer makes a fence along a river and has 100 feet of fence to do so. Oh, sorry. Instead of saying make a fence, I should say an enclosure. So the goal of this farmer here is to make an enclosure, a rectangular, I should say. So a rectangular enclosure along a river where the river will make up one side of this enclosure. All right. Find the largest possible, find the area, excuse me, of the largest possible enclosure. All right, so again, they're not asking for the dimensions this time, they're asking for the area. All right, let's go ahead and draw a picture. So that's step 1. Let's imagine that our river is right here. What we're going to do is we're going to use our fencing to fill in the other 3 sides of our rectangular enclosure. And they didn't give us variable names for this, so I guess I'm just going to call this X right here, and then this other side will be Y. All right, and then what we're trying to find the maximum of, or what we're trying to optimize, is area. So we know that the area is going to be X times Y. That's, of course, the area of a rectangle. Now, so that was step 2, writing down our equation. Step 3 has us eliminate all but one of the variables. Now, as we see here, we have 2 variables, so we need to get rid of one of them. And this is where the extra information in the problem comes in. This is where we're going to have to use that the farmer has 100 feet of fence to work with. So the 100 feet of fence has to build this fence, and this one right here. So we know that 100 has got to be 2x plus y. So what we can do here is, if we want to eliminate y, we can solve for y in terms of x. So we have 100 minus 2x is equal to y, and then we could substitute that formula for y into here. So a is x times 100 minus 2x, which we could FOIL out if we want to be 100x minus 2x squared. I think that'll be easier to differentiate. All right, we've actually come up with an equation that has 1 variable, so our final step is to take the derivative and look for our critical points here. So we're going to look at dA dx. So that will be 100 minus, let's see, this one being 4x right here. And this is a linear function or a polynomial, so we don't have any undefined points. So let's just set this equal to 0. If I add 4x and divide by 4, I get that x has got to be 25. All right, now remember, my goal was to get our area, so I have 100 times 25 minus 2 times 25 squared. So this will be 2,500. This will be 1,250. So we end up getting 1,250 for our maximum area that we can build, so long as we have the river fencing in one side. All right, so this is another example of an optimization problem. All right, I'm going to do one more example here. This example will involve some geometry. All right, find the area of the largest rectangle that can be inscribed in the unit circle. And I guess I'll throw in, let's find the dimensions as well. Occasionally, they'll actually ask you for both. They'll ask you for the quantity in question and the variable values that will give you that quantity. All right, so let's go ahead and draw a picture for this. So here is the unit circle. It's a circle of radius 1, and we have inside of it a rectangle. And when it says it's inscribed, this means that the corners of the rectangle reach out and touch the sides of the circle right here. All right, so this is our picture, but again, they don't give us any variables, so we have to make our own in this case. What I'm going to do is I'm going to draw this line right here. Now, since this is a circle, the length of the line from its center to the edge of the circle, where it also meets the corner of the rectangle, that has to be 1. And then what I'm going to do is I'm going to define this length here, dropping down directly towards the bottom of the rectangle. I'm going to call that length x right there. And as you can see from the picture, if you imagine that x gets, say, bigger, then we would end up with a situation like this, where this would go down here and we would have a larger x. Now, if we wanted a different rectangle, like say one that's thinner but stretches out further, we would make a smaller x. So by changing the value of x, we can end up getting all of the different possible rectangles that we can put in our circle. All right, so this is a good enough setup for us. Now we want to find the area of this rectangle, right? So the area is going to be the length times, the width times the height of the rectangle. All right, so we call it area is width times the height. Now, we want to define things in terms of the variable we have here, which is x. So we can see here that the height of this rectangle will be x, and then we just draw x in the other direction as well, so that our height will end up being 2x. So that's what our h turned into, 2x. Now we need to get what the width is. Now we don't know how long this is yet, but we can figure it out because this is a right triangle. So we can use the Pythagorean theorem to give us this length, which I guess I'll call a. So a squared plus x squared is 1 squared, or 1, meaning if we solve this, we get that a is the square root of 1 minus x squared. And I'll take the positive square root since this is a length. So we know that this down here is going to be the square root of 1 minus x squared, but that's not quite what we want. Remember, we want the whole width across the bottom. Now, a is going to be the width over 2, so this means that the width will be 2 times the square root of 1 minus x squared. That's going to be the width of this rectangle here. That's going to be a and then another a. All right, so now we can substitute that into here. And this will give us 4x square root of 1 minus x squared. This will be our area function in terms of this variable x right here. All right, we've accomplished step 3. We've gotten rid of all but one of the variables here. Now let's go ahead and find the derivative. So for this derivative is a little bit more difficult than the previous ones. I'm going to need to use the product rule here. So I'm going to do the derivative of 4x, which is 4. And then I'm going to leave the square root of 1 minus x squared alone. Then what I'm going to do is I'm going to leave the 4x alone and take the derivative of the square root of 1 minus x squared. Now the derivative of the square root of something will be 1 over 2 times that square root. But then we need to multiply by the derivative of the inside, which is negative 2x. So here is our derivative. All right, let's clean this up a bit. So we can cancel these 2's and move the negative here, combine the x's, and this gives us 4 root 1 minus x squared minus 4x squared over root 1 minus x squared. All right, so here's our derivative. Now we notice right away that we end up getting some critical values for x here. So we see that x equals plus or minus 1 are potential critical values. Now the problem with this is that if x equals 1, that would be the extreme version of this, where our rectangle went all the way down, but then it wouldn't have any width at that point, because our width would end up giving us 0 here. And the same will be true of -1, where you can maybe consider -1x moving upwards instead of downwards. Or you could also get away with not allowing it to be. But in either case, these critical points won't work. They're not going to give us something meaningful. All right. So now let's see if there's any critical points we can get by setting this equal to 0. Now, since we specifically said that x is not plus or minus 1 here, we can multiply both sides by root 1 minus x squared, giving us 4 times 1 minus x squared minus 4x squared. All right, multiplying this out gives us 4 minus 4x squared minus 4x squared is 0. So we end up getting that 1/2 is x squared by dividing everything by 4, adding this over here and dividing by 2. So after some algebra, we get that. And then we have the square root of 1/2, which means that x will be 1 over root 2, or as it's more commonly written, root 2 over 2. By the way, there's no reason why we can't write it like this, 1 over root 2. A lot of teachers insist we write it this way, but there's really nothing wrong with writing it as 1 over root 2 if we want. But anyways, here we have x is root 2 over 2. All right, so now what we're going to do is we're going to plug this in to our area formula. So a will be 4 times root 2 over 2 times the square root of 1 minus 2 over 2 squared. All right, let's simplify this. So 4 over 2 is 2, so we have 2 root 2. This will square to be 1/2. 1 minus 1/2 is 1/2. So these will cancel, and we end up with 2. All right, so that's the area, but then remember, this problem also asked us for the dimensions as well. So remember that the height is equal to 2 times x, so this will be 2 root 2 over 2, which will be root 2. And then the width will be 2 root 1 minus x squared, or 2 root 1 minus 1/2, which when we simplify, this will also end up giving us the square root of 2. So our height is root 2 and our width is root 2. Now that actually implies that since our side lengths are the same, that this rectangle is actually a square. So this square, drawing a square inside a circle, will give you the largest possible rectangle. If you make it elongated in any one direction, you'll be taking away from the area of this rectangle. All right, well, that's about it for today. I recommend watching Dr. Knudsen's and Dr. C's videos for additional examples about this. But as I said, every single one of these ends up being pretty similar every single time. We follow the same steps for all of these. But I encourage you to get some more practice. All right, that's it for this video, and I will see you all in the next video.